So, in a weird twist of mathematics, yesterday's lesson has nothing to do with today's lesson. So, good for you. Maybe Cody and Cody, if you need to adjust those blinds so you're not blinded by the lights there. Area under the curve. We are doing approximations. And I say area under the curve, I really should say, to be more specifically, area between a function and the x-axis. But it's easier to say area under the curve. And I know y'all took the notes on that and probably saw some of the vocabulary, saw some of the ways that we do this. There are lots of different functions that we are familiar with. We're familiar with linear functions, quadratic, cubic, all the flavors of the polynomial rainbow. All right, rational functions, radical functions, trigonometry functions, blah, blah, blah. But for the purposes of demonstration, just today, when I'm going to be talking about the area under the curve, we're really just going to be focusing on parabolas, okay, and quadratics, because it makes it real easy. And things that we see applied there, you know, or principles there can be applied to all the other functions, okay? But I'm just going to utilize quadratics and parabolas. So, I don't know, I'll just, kind of my go-to example is always something, you know, parabola opening upward, because I like to smile a lot. But anyway, we're looking at the area under that curve, f of x, and above the x-axis, so above here, and more specifically, I should say between f of x and the x-axis, and I'll add a little bit more here, and between points A and B. So A and B. Everybody knows that diagonal lines mean area, so. Looking for that area right there. So I said yesterday that we're going to use some pre-calculus methods, and I think y'all hopefully saw some of those methods in the book. Anybody want to tell us how could we approximate the area under that curve above the x-axis between A and B? Sure, Ivan?
There's the one where they like draw rectangles underneath it, and then they approximate the area of the rectangles. Or they take the area of the rectangles and they use that too. Yeah, absolutely, yeah. You break this down into rectangles, and then you find the area of those rectangles, and then you add them all up, and then that's going to be an approximation. This, absolutely. You take something that you do know how to find the area of, and you slap it on there, and then, yeah, now you could be, you know, really dumb with your number of rectangles, and you could just have one rectangle, right? Where it was like this whole thing, but clearly that would be too large, okay? So you break it up. You break it up into different rectangles, okay? The question is, how do you know how wide and how high you want to make your rectangles, right? You really could have every single rectangle be a different size. I could have one rectangle that was maybe kind of wide, but not very high right here, and then a series of really kind of narrow ones here, and then some ones that are in the middle there. I mean, I like everything to be neat and tidy, but it also is kind of helpful for mathematics purposes. It is helpful for us if we make our rectangles the same width. Something kind of like that. I haven't drawn them all the way up because that's the next question is how high do we go on these? But it's helpful if we have rectangles of the same width, and then we can just say this width times this height, this width, or I'll use the word base, I guess. This base times that height, base times height, base times height, base times height. You know, take all those bases and heights and then add them all up together, right? Now, did y'all, the question is, how high do we go? Did y'all see some, there's some different answers there.
on that? Did y'all see any of the different methods? I know you did because I saw it on your notes, but you might not realize that's what they were talking about. Let me help you out here. So when we decide what how high to go, one of the methods is called the right endpoint method, or you have right endpoint rectangles. And what that means is that the way that I determine how high to go on this is I kind of think of this first rectangle as having two endpoints. An endpoint here and an endpoint over there. And I'm going to pick the right endpoint and I'm going to go up until I hit the function. And that's going to be my rectangle. So it's going to be that point right there. That's how high I'm going to go. And then from there I just kick completely horizontally. And then with this rectangle right here, I'm going to pick the right endpoint and go up. And that's going to be the height of my rectangle. I'll go completely horizontal. Same thing here. And I'm just going to be consistent all the way across. I'm going to choose the right endpoint. And I would find the area of each one of those rectangles and then add them up, and that would give me an approximation for the area under the curve, above the x-axis, and between A and B. It's actually a pretty good picture, I like that. Now, one of the neat things, we could actually say some things about our approximation. What would you say about our approximation as it relates to the exact answer?
It's more.
Yeah, it's an overestimate. Okay. That's going to happen if you have a monotonically increasing function and you've chosen right endpoint rectangles. Okay? I want to draw not something that elaborate, but I want to talk to you about the other methods. Okay? For instance, the left endpoint rectangle method. So we'll draw that. And I think I should shove these over here for a reason. Yeah, they're okay. So there's A and there's B. We'll just divide this one up into maybe 4 groups. Left endpoint rectangles. When I'm making a decision, do I go up from the from this point to this point? We pick the left endpoint and then shoot across. And then for this rectangle, we use the left endpoint and I go all the way up until it hits the function, and then I go across. And then for this rectangle right here, I go all the way up until the left endpoint hits, and I go across. And for this, that's the left endpoint method for approximating the area under the curve. And if we had chosen this as our method, what would you say about how that relates to the exact answer? Yeah, it's an underestimate. So, if you feel like doing a lot of work, okay, what you could do is you could use the right endpoint method to get an overestimate. Then you could use the left endpoint method to get an underestimate. And then you would have some boundary. You could say, okay, I know the area is somewhere between these two. Okay? And that would be a thing. You could do that. Of course, it's only the right endpoint is only guaranteed to give you an overestimate if the function is increasing in that region, and the left endpoint is only guaranteed to give you an underestimate if it's increasing. Because think about if we had a function like this. You don't need to draw this one, but I'll just show you. You know, if we had left endpoint rectangles, then here would be you see how you start having overestimate as it was decreasing. When it was increasing, you were under decreasing is overestimate. So that plays a role. Did y'all see other methods listed in the text? other than left endpoint and right endpoint?
The midpoint.
The midpoint method, yeah. So we'll talk about that. This one doesn't seem to want to be used. So midpoint rectangles. So what you do with the midpoint rectangle is you find the midpoint between your the edges of your rectangle, and that's the guy that goes up. So you go and you go across like that. Here's the midpoint. There's the midpoint. And that's how high you go up. And if you draw it properly, you can pretty quickly see why a midpoint rectangles is definitely preferable. What do you think about that, Nick? Why would you say that is preferable?
Because there's like less gaps underneath the curve, which means like you need more.
Okay, yeah, I agree. The gaps underneath are a little bit less than maybe say this one, but also you have some area where some regions where you have overestimated, right? And you can say, well, that might kind of fill in this spot, and this might kind of fill in this. You see what I'm saying? So it might not be exact, but the idea is you're going to be a lot closer for just an initial. If you only have one choice, let's go with midpoint rather than those other ones. There are two other, there's methods for using rectangles, and those are the inscribed and the circumscribed rectangle method. So inscribed means you're not always going to choose the left endpoint and you're not always going to choose the right endpoint, but instead you will choose rectangles that are always going to be inside the curve. Okay? And the circumscribed method, circumscribed rectangles, they're always going to be outside. I'm going to draw a different function here. I'm going to draw something like that. Inscribed, you have to kind of deal with it on a rectangle by rectangle basis. You look at the two endpoints and you say, if I go up, which one of these is going to hit the function first? And right here, the left-hand side is going to hit the function first. So I make that my the point where I go up to. That determines my height. Right here, if these two go up, the left endpoint hits first. But on this rectangle here, when I go up, well, I guess it's still the left side right there. But right here, the right endpoint is going to hit first. And over here, the right endpoint is going to hit first. So I choose whether I'm going to use the left endpoint to go up to the function or the right endpoint to go up to the function based on making sure that my rectangles all stay inside. And this way actually is guaranteed to give you an underestimate, no matter whether the function is increasing or decreasing. In fact, that's why I have to have a region where it's increasing and a region where it's decreasing, and we're guaranteed that underestimate. The left endpoint and the right endpoint, those are really easy to use, but you're never sure if you're definitely always going to have an overestimate or underestimate. Okay, and then the circumscribed rectangles, I'll try to draw the same situation there. Upside down parabola. And in this situation, you basically would choose the other guy. You choose the endpoint that's going to always take you higher. So in that case, that's going to be this one. This one.
So that was a sheer overestimate.
Absolutely. Yep. And there was one more method. I'm not sure if your book talked about it or not. It wasn't using rectangles. Did the book talk about the trapezoid method? Let's talk about trapezoids. You may remember trapezoids that look like that, right? Where basically a trapezoid is a quadrilateral that has two sides that are parallel and two sides that are not parallel. Okay? Well, you could also turn that sideways. I mean, isn't that a trapezoid?
Mm-hmm.
Well, isn't that also a trapezoid? We've got a right angle right there. You have two sides that are parallel, two sides that are not parallel. Okay, and then you could also have a trapezoid that would look like that, right? And so the trapezoid method is an awesome method, and we'll let it review this, okay? The trapezoid method says, go up with the left endpoint and with the right endpoint. Go up to there, go up to there, and then connect them with a line, a straight line. Left endpoint, right endpoint. Connect with a straight line. I don't like that straight line. Whoa.
So that's the most accurate one.
Yeah, it is. Look at that.
Dang.
Your calculus is doing pretty good, huh? Right? So, the trade-off, as we'll see, is you've got to figure out what this base is and this base and all that stuff like that. Does anybody remember what the formula is for the area of a trapezoid? It resembled a triangle and a rectangle, kind of. It's 1/2 base times height. But there are two bases in this case. The bases are the parallel sides. So that's like base 1 and that's like base 2. And it's 1/2 base 1 plus base 2 times height. So to approximate the area under the curve but above the x-axis and between A and B, you would find the area of trapezoid 1, then you would find the area of trapezoid 2, then the area of trapezoid 3, then the area of trapezoid 4, then the area of trapezoid 5, and then you would add them all up together, and then you would have pretty close approximation to the exact area. Alright, how are we doing so far? Pretty good? Just a matter of, you're like, I know it's going to get hard somewhere. It really isn't. It's just, we're going to add up area of rectangles and trapezoids. That's all we're going to be doing today. So, no problems, right? We can find areas of rectangles, base times height all day long. So, one decision that you sometimes have to make is, how many rectangles do I want to make? right? I chose, how many did I have? 3, 6, I chose 10 rectangles there. That's gonna be a lot of work, okay? But I should get a pretty good answer from that. I could have chosen just, 2 rectangles. I could have chosen like this one here and that one there. Of course, there's all sorts of problems with that. What's the problem with trade off, right? Everything's a trade off in life, right? It's easy. I only have 2 rectangles, but what's the trade off? Yeah, it's not very accurate, right? Okay. That makes me wonder, what if I was willing to do a little bit of extra work and made it into 20 rectangles? Yeah, that'd be better, right? What about 100 rectangles?
Holy cow.
A lot of extra work, right? But
It's worth it.
accurate, because those rectangles would be like, it'd be even smaller than this. This is like 20. But you know what I'm saying? What if I chose 1,000 rectangles?
Holy cow.
I mean, at that point,
Right?
especially if you're using midpoint.
Yeah. But you know what? Maybe I can just get a computer to do all that stuff. Yeah, okay. Getting, so now there's a couple things that change when I do that. One is clearly my overall answer is going to be more exact. But also, as you noticed, the width of those rectangles, or maybe you can think of if it's the base and this is the height, the base is getting smaller, right?
Mm-hmm.
Okay. I wonder if we could figure out, or I'll just tell you here, there is a formula for figuring out how wide that needs to be, okay? All right, and here it is. It's whatever the distance here is, the length, okay? So the width, or I'll say the width of a single rectangle equals the whole length divided by the number of rectangles. See if that makes sense to you. For instance, if that whole length was 50 units, right? And I wanted 10 rectangles, then what would the width be of each rectangle?
5 units.
5 units, right? That seems to make sense, okay? So, how can you tell the different distance between A and B? If those were actual numbers?
Add up all the rectangles.
No, I mean like, what if I said this was, so this was 3 and this was 10?
Oh,
Subtract.
you could.
Yeah, subtract them, yeah. So here's the actual formula. So, rectangle width, since this is on the x-axis, we call that delta x. So delta x equals b minus a divided by n, where n is the number of rectangles. If you don't have a calculator, go and grab a calculator. Okay. Tomorrow, we're going to get calculus up on this, and we're going to see what happens. What is going to happen to that area as the limit of the area as the number of rectangles approaches infinity.
Holy cow.
Right? Because I said, like, what about 100? What about 20? What about 100? What about 1,000? What about 1,000,000? Okay. Well, I can tell you one thing. What's going to happen with that width?
It's going to approach 0.
It's going to approach 0. Okay. So what we're going to do tomorrow is we're going to have rectangles that are infinitely small in their width, and we're going to have an infinite number of them. but we're gonna add them all up. Didn't think you could add up an infinite number of things, right? It's gonna be a really long class tomorrow. But we're gonna, but actually, you say, ha ha ha, you know, that's what the limit does, and we have algebraic ways and graphical ways of evaluating limits, right? Even if they go to infinity. That's where we're going here, okay? Now, on today's homework assignment, you do not have to choose the number of rectangles. I've already chosen them for you. I've even drawn graphs for you, okay? And I've even done, what else? I've done all kinds of stuff for you. So all you're like to do is just figure out the areas of these rectangles, okay? But keep that in mind. Have that formula right there. That's the formula for the width, okay? And let's go ahead and start doing some problems together. Mm-hmm. All right, for each problem, approximate the area under the curve over the given interval using 5 rectangles, and they say some other stuff there too. There we go. So here we have the function, negative x squared plus 12, and we are interested in the region from -2 up to +3. And what method have I chosen here to create my rectangles?
It's actually, what's it called?
Midpoint. The left.
It's the left endpoint is what I've done. So there should be 5. Are there 5 rectangles here?
Yes.
So you kind of think of like, this is one of them. That's the endpoint.
So it's locating over and underestimate.
Well, it's not guaranteed to be an underestimate unless it was strictly increasing. But here we have something that's increasing and decreasing. So in the increasing, we have a little bit of an underestimate. In the decreasing, we have a little bit of an overestimate. So it's just kind of whatever. So let's go ahead and first figure out. So this is the first rectangle. This one going all the way down there. So I'll say area of the first rectangle is. Now, like I said, I've already chosen the number of rectangles. It's 5. You're welcome. And I've done that because it makes it real easy to figure out some of these things. What's the width right there? 1, right? Which we also could have done if this is A and this is B, and we did B minus A divided by N. That would be 3 minus -2 divided by 5, which is 5 and 5, which is 1. It's a width of 1. Right? Okay.
Wow.
And we're going all the way up to this point right here. So I need to figure out, I've got the base times the height. Well, the base is 1. How am I going to figure out what the height is?
John.
It looks like it's 8.
Yeah.
But, did you say plug it in?
Yeah.
Yeah, that's the right answer. Good job. Let's go ahead and plug in -2.Maybe just key that into your y equals editor. Or in your head, I'm going to plug in -2. So negative 2 squared is 4. -4 plus 12 is 8. So 1 times 8 is 8. That's the area of that first rectangle.
You do that for each rectangle.
Yeah, we're going to do that for each one of them. So base, that's this distance right here, which is 1. The height, it looks like it's 11.
We must plug in.
Let's plug in just to be sure, so we're going all the way up here. -1 squared is still negative, is 1, but negative right there, so -1 plus 12, yeah, it's 11. Now, on this particular problem, everything is real nice and the boxes are all there, but I think if you look through the homework, some of them aren't. I don't know, maybe they're all ending at the boxes. Are they all ending right on the ending at the... Yeah, there's some of them that aren't, even on as early as number 3. That's okay, we'll get to that. I left lots of room under there for you. So the area of rectangle 3, That goes up, we can plug in, this is the left end point of 0, so we can plug that in. 0 squared, so plus 12, so it's 12. Area of rectangle 4 is 1 times 11, again. 11. And area of rectangle 5, 1 times 8, so that's 8. And then area total, 8 plus 11 plus 12 plus 11 plus 8. What's that? So that's 20 plus 22. Is it 42? 50? What am I doing wrong here?
Good. Let's see, 8 plus 8 is 16. And then 12 is 18. Yeah, 18 plus 10 is. Or, wow. 18 plus
50.
12
Why am I thinking? Did I skip one? 20. Oh, I forgot the other 8. Well, it's 42, but I forgot the other 8. That's why. Okay. 50. That's great. Number 2. What sort of rectangles? Left end point, right end point, midpoint. Left end point. Yeah. I'm gonna try to do one of each together. Let's look at number 3. What type of rectangles are there?
Right.
Yeah, that's the right end point. So let's go ahead and do one of those, shall we?
Yes.
And it's kind of annoying. It's not exactly at the box stop. You know.
Oh yeah, that's true.
All right. Still 5. Okay. I think this one is a 3. Should we plug it in just to be sure?
Mm-hmm.
So I'm going to plug in -2. So the area of my first triangle. Well, it's still a width of 1. And if I plug in -2 to that formula, so -2 squared over 2 plus 1. So 4 over 2. So 2 plus 1. So yeah, that's 3. This is really what I want us to get here. How am I going to figure out how high this one goes? Plug what in? -1. Do you see where she came up with that? Because it's going all the way up to the function from the x value of -1. Okay? So a little side problem here. -1 squared over 2 plus 1. So 1 over 2 plus 1. So 1.5? So a base of 1. I would really recommend you write the base, even though it's been 1 for a lot of these. Still just write that out so it'll reinforce in your mind that we've got a base times the height. Okay? And it'll prep us for tomorrow. So.
Why do you have a 1 for A1?
Because I just have to write 1, that's 1. Area 3, Stephanie, if these are right endpoint rectangles, so how am I going to know how far to go up?
Plug in 0?
Plug in 0, that's right. So 0 squared over 2 plus 1, so that's just 1. And the fourth triangle is 1 times, if I plug in 1, I get 1/2 plus 1, so 1.5. And the fifth rectangle, there's a certain symmetry going on here, so that's going to be 3. So 3 plus 3 is 6, plus another 3 is 9, plus another 1 is 10. So the total area, I put approximations because it's approximately 10. Do you think we have an overestimate or an underestimate, or do you think we're spot on?
Well, I don't think we're spot on. But, let's see.
So what do you think on this one? Think we've got an overestimate or an underestimate on our hands?
Over. Oh.
Maybe you might think we're spot on, because you're like, oh,
A little triangle goes.
there's so much symmetry here. Maybe we're exactly right on. Now we're not. Okay? Oh, and 10's such a right answer. Yeah, it is a right answer, but it's not the exact answer. The exact answer, if you were to apply the limit process to this, you would get 10.833 and I think a whole bunch of other threes after that.
So
It's an
underestimate.
so we've got an underestimate on our hands right there. Yep.
Yep.
Not by a lot. Like 1.8333 repeated off, but yeah. But 10 to, we're pretty close. All right. So I was planning on doing as many of these odd problems as possible. Okay. And this is a good one for us to do next. Number 5, this midpoint problem. Okay. Now, we just really lucked out. Everything's from -2 to 3, and there's 5 rectangles, and the width is 1 on all of them. That's awesome. So I know it's going to be 1, but now we've got to figure out what's the height for that midpoint. See what I'm saying?
Yeah. Do you go to 1.5 and plug that in?
You would plug in -1.5 because you're thinking because this is -1 is negative 1.5, and plug that in to this. Absolutely. So now what I would do is I would type this into your y equals editor and then just maybe go to the table or go to the graph to plug that in. Because it's going to be -1.5 squared minus 2 times -1.5 plus 2. Does that make sense?
Yes.
So you're just going to have to literally plug that in. Now you got Desmos, you can plug it in that way as well, or you can just key it all in. But we're going to have to do that for this value, we're going to do it 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 for that value. We're going to have to plug in all of those midpoints, and it's kind of yucky there. Anybody have a number on 5 for that first height? Say again?
7.25.
7.25. The area of this next rectangle, I'm going to plug in -0.5. Somebody tell me real quick, what value are we going to plug into that third rectangle? Positive 0.5. Yep, I agree. Then plug in 1.5 and plug in 2.5. Nick, do you have some numbers here for us?
No, my calculator.
Oh, let me swap you out.
Huh? This one's on.
Will it work though?
No,
Oh.
and I have a little better.
Anybody have some numbers here? Hector, you got a number here for area of region 2?
No, I don't have a calculator because that one didn't work.
Oh, okay.
It's a 3.25.
3.25? Need some numbers for 3, 4, and 5, or can I just leave this to y'all to take care of for homework?
I have them if you want them.
Sure, go ahead and call them out there to us.
1.25, 1.25, and 3.25.
Now the nice thing is when you multiply those by 1, then they're just the same number. And then when we add them all up, I'm using the approximation symbol because this is an approximation. What do you have, Emily?
16.25.
16.25?
Yep.
What do you think, overestimate or underestimate? It's an under. Yeah. What I'd like to do is I'd like to have the same homework and then like, we'll do all these problems again, but with like the
More complicated.
yeah, the more complicated one. Okay. You get the exact answer, okay? Alright, that's great. We're running low on time, but that's okay. I think for number 7, y'all can look at that and what type of situation do we have there? What sort of rectangle choosing method did we have?
Oh,
It's the inscribed.
It's the inscribed, right? That's great that you can recognize it, but that just means that sometimes you're just gonna kind of have to do this on a rectangle by rectangle basis. I went to the left side here, I went to the left side here, I went to the right side here, I went to the right side here, I went to the right side there. So if you can do left endpoint and right endpoint and midpoint, then you can do circumscribed, or rather inscribed, and I'm pretty sure you can handle, like number 9, that's a circumscribed. But what we definitely need to do is number 11, right?
Yeah.
I don't tell you, but that's using trapezoids, okay? So let me tell you how this is gonna work. You're gonna, the formula is area 1/2 base 1 plus base 2 times the height. And base 1 is going to be the left side of the rectangle, and base 2 is going to be the right side of the rectangle, and the height is what we would call the base previously, but this width right here. So the area of trapezoid 1 is going to be 1 times, you're going to have to plug that number in. Is it 5? I don't know, it looks around like it's around 5. But whatever that value is, base 1, plus you would, and the way we would get that is we have to plug in -4. Then we would plug in -3 to figure out how high we were going here. And then, put a 1 right there, I'll put a 1. 1/2, base 1 plus base 2, and then you would have a height of equal to 1. Look at that and see if anybody has a question on that. Sorry we don't run out of time here. But you would just do that for trapezoid 2, 3, 4, and 5, and then add them all up. So in this case, you have to find left endpoint, how high would it go, right endpoint, how high would it go, and put those numbers in here.
So you basically plug in 2 values for each.
You plug in 2 values. Now the advantage is for the next trapezoid, this trapezoid's left endpoint is the same thing as this trapezoid's right endpoint. So you're not really having to figure it out, twice as many. It's just technically just really just one more endpoint. Does that make sense?
Yeah.
This homework I think is going to be due Monday.
Okay,
Alright. That was area under curve using approximations. Thank you, Stephanie, for the help.